Charger Professional with the updated discharging and also control on each IC for charging. The PCB is finished now. This is how it looks. Before we had 4 PCFs on the back. Now we have only 3 ICs to control everything, because this bigger one, I say bigger because it has more pins than the others. So this one has 16 channels. That's perfect for our setup, for our 16 cell setup for Megacell charger. This will generate the PWM signal for each cell. So we'll be capable of setting discharge, a discharge rate per cell. And this will allow us to implement constant current and constant voltage with the PID to keep the constant current and also the constant voltage. We'll also keep the constant resistance as well. That will not change, but it will change the ability to let me fix this one here. Where is it? Oh, the bottom layer. So here I must add a via. Okay, that's better. So I was saying that it will allow us to set a discharge rate per cell if we want to. At the beginning we'll set it to all the 16 cells, but in the future we will add it per cell, most probably. So that's all. Now the constant current, constant voltage for discharging, and also communicating with each BQ24195 IC, which is this one right here. And I'm also seeing some large font texts here. This is a resistance. This is for the resistors I added for the communication. I will fix that. Let me touch it up now, actually, because tomorrow I want to generate, I want to sleep over this in case I I wake up with any other things that I want to add, but I don't think it will be the case, actually, because I pretty much added everything I had in mind. This communicating with each IC, with each BQ, it was giving me headaches from the beginning, and I was finding ways to not implement this, because I knew I had to change the whole communication lines, and also the software and the way I communicate with the ICs, it will be different. So belongs to layer. Is this on layer top overlay? Where is my query? So I was, as I was saying, it was giving me headaches. I could not communicate with each IC and I was trying to fight against making the entire change because I knew it will add a new layer of difficulty in releasing this project. But after I finished the other changes, this seemed like the next step that it had to be done in order to get the events we have from the charging IC. It will make the process much it will make it easier to check every step to make sure that we're having it will be like a pre-flight checklist where we check everything. We check the IC for events. We check that we have a good voltage battery. We check that we have a good power supply. That's also something that we can check from this IC, because if the voltage goes under 3.8 volts at the input, we can check that from the IC and say, okay, we have a bad power supply, you cannot charge this. We can set a limit current for the IC. So there's a lot of things that there's a lot of features that this IC is allowing us to use in this charger for the charging on this device. So if you want to get all the information, I don't have a documentation for the Megacell charger, for the updated Megacell charger yet, but I plan to implement that after we finish with getting everything together with the software and the hardware as well. But if you want to get a peek on the features that we'll have for charging, you can open the datasheet of the BQ24195, and that will give you a pretty good idea on all the things that we can do using this IC. So this belongs to this one. Yeah, this looks boring, but it's very helpful when you're using this layer for assembling the parts. You either do it manually, or if they are done at the factory, they will ask less questions about where these parts can go. Because even if you're generating the parts for the assembly, some of the parts might be twisted, or it's double checking to make sure that the part placement file corresponds with what it should be on the final board. So I want to get this as close as possible, make it readable. It's like a map that you use when when assemble the components. So let's put these ones in place as well. So that's what actually I wanted to say, that the board is finished. I had to go earlier, I had to get some lunch, and I also had to finish moving some things, because I moved from the place we stayed before to a place that's actually outside the office. So I'm in and out now. Before I was spending like 15-20 minutes going back from work home, and also enjoying the traffic sometimes where it was rush hour. It's not a big city here. We don't have rush hour like you see in the bigger cities where you spend 2 or 3 hours in traffic. I could not stand that, actually. When I'm going to Bucharest sometimes and I see that traffic, I tell to myself that I will never live in a city like that. There are some benefits in larger cities, more connections, more things to do, but for now, small town works fine for me. So yeah, I had to finish moving the stuff and also finish some packages I had to ship. But things are going fine. Getting back into this project now looks like it's the right time because we have access to the components. We field tested the Megacell charger so far. Where I place this one? 6, 9. All right. So we field tested the Megacell charger. We know what works, what doesn't work, what can be improved, how to improve it. So this looks like the next step in getting everything done, everything that we learned about from different tests we done ourselves, from different ideas we had from clients. I actually cannot place that up there. Okay. I realize that there are the pads. Here is the pad for the small coil that's required to generate the voltage. And I wanted to make something, to implement another feature from the BQ, and that's the ability to generate voltage from the battery. So this IC is mostly used in laptops or devices where one cell, I don't think there are any laptops with one cell like 4.2 volts, but there are devices where you have just one cell that you want to manage, charge and discharge. And this IC can boost the voltage. So if you had 4.2 volts and wanted to charge a phone from this device, it needs to boost it to 5.1 volts and keep it there stable, even if the voltage will drop on the cell. So I wanted to use that to generate a voltage that could charge another cell. There were some requests. It was just one request actually, but it was a smart thing. It was something that could make a difference from some users that wanted more control on the device and wanted to not waste the power from the discharging. So instead of generating the heat with the resistors and being, you are somehow limited on the discharge rate by how many amps you can discharge on the resistors. For now, I tested up to 3 amps and I got 140 degrees on, around 135, 140 degrees on the resistors on the back, and that's on the safe side. They can go up to 160, 170 and not damage the PCB. We're considering for higher amp draw, we might have to change the fans, but for now we're going to set it to 3 amps, the max limit. That's more than enough for most of the cells, and if you want more, you can combine the slots together to discharge higher amp. There's also a limit on the wires that are used for the accessory. You cannot place too thick wires on the pins on the XS12 connector. That's also rated for 5 amps. So the connector for the XS12, let me double check that. It's either 5 amps or it's 3 amps, but I think it was 5 amps. 12. Yeah, it's actually 3 amps. So that's also one reason we should keep this at 3 amps, because if you want to discharge with more amps, you will have to place wires directly on the back of the PCB. So yeah, that's another thing that I will add. It's some pads that you can solder thicker wires on the back of the PCB if you want to output voltage. So as I was saying, I wanted to get this, it's called PMID on the BQ if you're checking the data sheet there. So I wanted to implement that, but there's a catch actually, because that device is made to generate power when there's no power input. So that would mean we have to disconnect the power from the charger, from the top of the IC. Let me clear this. So here we have the 5 volts rail, or 5 to 70 to 16 volts rail up top here. There's a 0 ohm resistors that is pushing the power into the input here. So we had to stop this power and provide the power from the cell to the IC in order to use the PMID functionality that this IC offers. And that's not easy to do, and it doesn't make too much sense, to be honest, to do it this way, to disable the power input. I have to set the IC again, and if the cell gets removed, I will have to enable the main power again so I can communicate with it, and it's going to be a mess to actually use this kind of feature from the PMID. But I thought about a different solution to use this, and it's also easier. So that will be soldering directly on the discharge. Let me show you here. So on the discharge pads here, we have enough room to place a pad that will remain uncovered, so you can solder wires to it, and then you place the connector from there. And I will also get the gate, add a pad for the gate as well, so we can get the information from the IC that, okay, I want to discharge this. We can start the accessory to start drawing power, maybe charging a cell, or maybe dissipating in a bigger heatsink with resistors and all that. So that's something that I look forward to test as well. And there might be some people that will enjoy this feature just to play with it, or maybe the commercial versions when discharging a 50 amp cell. That's how many watts? That's about 200 watts of power. If you discharge 5 of those cells, then if you make multiple cycles, you can save around how much? About 50 cents on the electricity, depending where you live. But for us, it's like 35 cents per kilowatt at the moment. From this perspective, it doesn't make too much sense. It will require more accessories, and if you're not a big company that discharges thousands of these cells, and you want to also get the environmental part in check as well, because you don't want to waste electricity testing cells, electricity that's produced from other kind of energy sources other than solar panels and wind turbines. That would be a nice feature. It will be on the data sheet. You can use it if you want to. If not, no problem. All right, this one goes, let's place it here. Okay guys, so that's about it for the part 2 of the video as well. You see I'm still touching up this PCB because I just got it finished, and I had a look in 3D and saw that these texts were not placed correctly, and you could actually not see what I was doing. You could only see my face. But what I did is I started placing the texts for the components, placing them properly so they are visible when this PCB gets assembled. This one is a bit far away, but it's too long to keep here. So I had to add these 2 resistors on each IC. This is for SLC and SDA, that's the communication. So these 2 resistors had the labels placed incorrectly. I had to redo those as well. Okay, let me check the bottom ones as well. Because I know I added some there. Error is activated. So I was saying that during assembling manually or at the factory, you will use these labels to figure out which component must be placed where. This one is left. I burned 2 chargers so far, testing different things on them. One just blue. Let me get the picture. Or is it? Hmm. Ah, this one. So it just toasted. I was hooking up the discharge, the BK precision power supply discharge supply that I have here, this one. So I hooked that up, and I think the ground was common with the 12 volts power supply that I used, and somehow it got energized a lot, and this happened. Like all the connected BQs, I had 4 of them connected because I was testing the communication stuff, and they got toasted instantly like fireworks. So let me show you some of the videos I did testing the temperature for discharging.
Test la 1,1 ampere.
Okay, so this one is 1.1 amps.
Ventilatorul este dat să bată spre...
So this is 1.1 amps, and also the bottom cover was out because I had to film this. That also has some impact on the airflow. It will make sure that the air is pulled from within the case. With it open, it will pull air from the sides as well. But still, it's showing the temperature that we have, and that's what I wanted to see. When we cover it, it will improve the airflow, and it should improve the temperature as well. So this one is 1.8 amps. You see the bright point at the bottom. Let me stop it when it's there. That's the MOSFET. This one. That's the MOSFET that we use. But the MOSFET is not actually getting this kind of temperature when it's not close to the resistors, to the discharging resistors, because we have such MOSFET on the front that's used for reverse polarity protection, and both MOSFETs receive the same current draw, and that's on the back, because the PCB is hotter, it cannot dissipate the heat fast enough to keep it cool as well. But this MOSFET is good till 150 degrees, and that will keep it on the working conditions tested in the datasheet, because they test it up to 150 degrees, but it's more likely to burn when it gets to 190, 200 degrees. But with improved airflow from the lead, it should stay within the range. I looked for different MOSFETs, but this one is the right one for the design we have, because we're using low voltage gate control, and other use like higher voltage, 8, 12 volts, and we have to change the design to accommodate for such voltage for gate control. but for now it works fine, no issues with it. I could not burn this resistor so far. I'll do multiple tests after I get the final PCB, and in case I have to update the fans, I will upgrade the fans for the rated current that we're going to place on that charger. We might sell a version that's rated to 2 amps, and we might have another version that's rated up to 4 amps with improved fans for better airflow. The thing is that if we are upgrading the fans, the reason I'm not upgrading the fans on all the devices is that that the bigger fans, it's not the bigger fans, it's more powerful fans, will make a lot of noise when they are spinning faster. If they are spinning at 2 or 3,000 RPM, you'll get a lot of noise from those fans. So this is 2.4 amps. So I will do more tests like this in the future, checking that we're staying in spec, we're analyzing what's happening with the device, if there are any issues with the traces. I upgraded the traces from before. Here we had a thinner trace for the power dissipation, but now that we amped the amperage drawing, I thickened that as well, here and here as well. So we have here you have the shunt that's measuring the noise. Here's the cap. On the front we have the shunt. Alright, here. And the board is flipped. It should be on the back, but it's strange sometimes when you flip the board. Now here is the shunt, here is just a cap. When you flip the board, sometimes you lose the place where you are at. So yeah, this one is the shunt that's measuring the current drop, and this one is a capacitor that's 10 microfarads. Yeah, I learned a lot about PCB design lately. I had some experience from before. I designed a board for a miner in 2018 when the Bitcoin, like it got up in price like $16 or $18, and people were freaking out, wanting miners. So I designed my own board for a miner. But after that, other companies released like very fast new miners. But I had a lot to learn from that project as well. I learned a lot about parts, components, how to design a PCB, how to lay out parts, how to order the parts, how to test that everything works properly. So yeah, that's what I learned from that project, the whole process of getting everything together and getting the final product. It's very satisfying to see the physical product processed after you finish drawing. Make sure that everything is up to the spec that you design in the schematic, and also check the data sheet as well, because there are some components that are required to be installed, and the way they are laid out. On some parts you need to put a capacitor next to the main IC, because otherwise it will make fluctuation. It will fluctuate the current or the voltage, and that will cause issues that you will not know where they are from. So you need to make sure that you follow the design rules, and also after you finish the board or finish the layout of the parts, you run the design check, and this is what you want to see here: 0 warnings and 0 rule violations. And make sure you have all the rules created properly for the hole sizes, silk to silk, and also need to have the short circuit. This one I think is the most important one, because if you have short circuits, that design will not work. So that will be all for this video, guys. I'm going to sleep on this one. Make sure again, I will check it again tomorrow, see if I missed anything in placing the components in somewhere. I will double check the schematics, and then I will generate the files, the production files. So here we have the diodes. Here I had the switch, but that got replaced now with this component here. Actually this one, yeah, this one is the component that will handle the switches. So I changed that with electronic switch and no longer have to fiddle it manually. I also had to, if I would have kept that design, I would have had to modify the case, and I did not want to do that actually, because it's a simple, it may look like a simple process, but to do it right and place the hole where you need it, and also have the users not to rip off that small switch I added there, it was sketchy. So I'm glad we ditched that. We replaced this with a component. We also have a few other channels that we can use in the future if we want to drive different things. And also the ESP32 on the back here, that will be populated later when after we finish developing all the features in the software, and there's nothing left in the logical part of the software. We will move the code to make it work for ESP32 as well, because this will allow us to evolve and make this project, bring it to the next stage. That will be communication through Ethernet port, also maybe Bluetooth device to connect with your phone easier to it. You could connect to it via Bluetooth, then set the Wi-Fi from the Bluetooth application. That will streamline the setup process as well. So you could set the Wi-Fi, you can have the Ethernet port and also Bluetooth to check the connectivity, set the IP, set the network details, and other things that you want to do quickly. So Bluetooth is for fast connection, Ethernet and Wi-Fi it's for usage, so usability. When you're transferring a lot of data, it's better to use the Wi-Fi or the Ethernet and not the Bluetooth. Bluetooth is for small apps that you would use to set it up. First word, quick control. Yeah, you could have the quick control like start charging, start discharging, but you cannot get data from it. Again, guys, thank you very much for watching. Thank you for your support. And if you're not a subscriber yet, please subscribe to this channel. I'm not used to saying this, but I will have to say it because I see people are not subscribing if they're not told to. They might say, okay, it's not very important to do this, I will check it later, but it's actually important for the YouTube algorithm because it will flag that that channel is providing good information for this kind of users, so it will show this channel more frequently to other users as well, which might find this useful and which might interest them to learn about what we're doing with the batteries, why we build this product in the first place, how we're using it to test recycled batteries. So yeah, please subscribe, hit that notification bell. Hopefully you want to learn more about this in the future, and stay tuned, so get subscribed now. Thank you very much for watching again, guys, and have a great evening or have a great day depending on the part of the world you are at. Goodbye.